I want to start off with a quick refresher on spherical coordinates. In particular, I want to talk about how to think about them geometrically, how to convert between Cartesian and spherical coordinates, and then more importantly, how to use them in triple integrals. So what are spherical coordinates? You can think about them as a three-dimensional analog of polar coordinates. In 2 dimensions, polar coordinates gave us an alternative way of describing points in the plane, using an angle and a radius. So naturally, this is a circular way of thinking. Similarly, in 3 dimensions, we can think about points in a very spherical way, and this gives us an alternative coordinate system where the variables are rho, theta, and phi. So what do these things represent geometrically? Suppose I have a point sitting in 3-dimensional space. Similarly to in polar coordinates, rho is the radius. In other words, it's the distance from the point to the origin. The next variable, theta, is actually the exact same theta as in polar coordinates. That is to say, it's the angle of rotation from the x-axis in the xy plane. So by that I mean if we take our point and we project it onto the xy plane, I would get some ray like this. And theta is the angle that that ray makes from the positive x-axis. Finally, we have another angular coordinate, phi. Phi is the angle from the positive z-axis to the point. So we want to think about phi equals 0 as being the z-axis, and then we sweep out towards the point. An important thing to talk about is the ranges of these coordinates. Just like in polar coordinates, the radius rho we typically want to think about as being a positive number. In other words, we start at the origin and walk outwards. Theta, like I said, it's actually exactly the same as in polar coordinates, so its range is from 0 to 2 pi. At 0, we start at the positive x-axis, and then we can swoop out the whole xy plane with a range of 2 pi. Phi, we actually only want to range from 0 to pi. So at 0, I start with the positive z-axis, and then I swoop down until I hit the negative z-axis. And we don't want to think about sending phi from 0 to 2 pi. Now, a good question to ask is, well, Joe, what if I wanted to get to this point back here, for example? How am I supposed to do that if I can only go down to pi? And the point here is that you can use theta. So instead of overextending the phi angle, you can just reposition yourself with theta so that I point this way and swoop down from here to here. Okay, the next important thing about spherical coordinates is how they relate to Euclidean coordinates. And just like with polar coordinates, this boils down to trigonometry. So I'm not going to prove these, or I'm not going to explain where they come from. But if you haven't done this yet, it's something that you should sit down and think about for yourself, because it will really reinforce your understanding of spherical coordinates. Anyway, I would say there are 4 main equations that you should know. One of them is that rho squared is x squared plus y squared plus z squared. This is just the distance formula, and it's the analog of r squared equals x squared plus y squared in polar coordinates. And then we want to have equations for x, y, and z in terms of these new variables. X is rho sine phi cosine theta. Y is rho sine phi sine theta. And z is rho cosine phi. Like I said, I'm not going to explain where these come from, but one thing I'll point out is that if you look at the picture, rho sine phi, this is exactly r. This gives you that length of the orange ray in the xy plane. And remember from polar coordinates that x is r cosine theta, y is r sine theta. That's still the case here, nothing's changed. We've just extended into a new dimension. Finally, and maybe most importantly, is we want to talk about exactly how to convert a Cartesian triple integral into one in spherical coordinates. Now, just like with polar coordinates, this is just a change of variables. It's just a particular change of variables. So if I start out with some integral over a three-dimensional region E in terms of x, y, and z, when we change this, what do we have to do? Well, one of the things we have to do is change the bounds. So by that I just mean we need to figure out how to describe the region in spherical coordinates. We need to change the function we're integrating, which is going to make use of these equations. And we need to change the differentials. The differential changes by multiplication by the Jacobian. And it turns out that the Jacobian of the spherical coordinate transformation is rho squared sine phi. Again, I won't go through this computation now. This is something that you can sit down and compute yourself. It's a little tedious, but it works out. And for something like a spherical coordinate transformation, it's something to just remember. And there we go. That's how we convert a Cartesian integral into one in spherical coordinates. And that is pretty much all you need to know in order to do some examples. I want to start off with an example that's relatively more straightforward, and then we'll do something more complicated next. But in this one, I'm giving us a region E. It's in the first octant, bounded by a bunch of stuff. X equals 0 is a plane, y equals x is a plane, x squared plus y squared plus z squared equals 2. That's some kind of sphere. And then a cone, z squared equals x squared plus y squared. And our end goal is to compute some triple integral of 1 over x squared plus y squared plus z squared dv over this region. Now, this is something I've talked about with polar coordinates before, but in the statement of the problem, I haven't said anything about spherical coordinates. You could come across an integral in real life and it's not going to tell you, psst, by the way, use spherical coordinates. So a good thing to do is to get a problem like this and go through the motions of thinking about why this is a good idea outside of the context of this being a video about spherical coordinates. Now, just like with polar coordinates, to me there are two main indications that this is a good idea. One of them is anytime you have a spherical region, and in this case we do. We have a sphere as part of our bound. And then cones, to me, also count as spherical type objects. And another indication is if you have something like x squared plus y squared plus z squared in your integrand, because this behaves so nicely with spherical coordinates, that's another indication that this is a good idea. Okay, so as always, I'm going to start off by drawing a picture. Now, trying to draw pictures of regions like this in 3 dimensions can become a little disastrous, so I'm going to draw a couple pictures. I'll try to draw the whole picture in 3 dimensions, but it might be a little confusing, so I'm also going to end up drawing a side view. And thinking about projections of the region in general is a good thing to do. So here's our first octant. One of the bounding surfaces is x equals 0. That's the YZ plane. One of them in green is y equals x. Now in the xy plane, that would be a line like this. So the plane just extends in the z direction. We get something that looks like this. Then we have this circle in blue. This is where the sketching can get a little tricky, so a good idea is to draw traces in planes. And because I care about this stuff between the green plane and the red plane, I'll draw the trace of this circle in each of those planes. Then I'll draw the trace in the XY plane, and we'd get a picture that looks like this. And you know, the sphere itself extends beyond this little region. It goes over here, and it's an entire sphere. But we only care about what's happening in the first octant, and we only care about what's happening between the red and green planes. Finally, we've got the cone. Again, this will be a little difficult to sketch in its entirety, so I'll draw traces. For example, in the red plane, which is given by the equation x equals 0, we would get the equation z squared equals y squared, which in the first octant boils down to z equals y. So we'd get a line kind of like this. Similarly, in the green plane, we'll get a line like this. We're describing a cone here, so the angles are all going to be the same. And then, the cone connects something like this. So since our region is bounded by all of these shapes, and the problem specifies below the cone, that means the region we're interested in is this stuff right here. Now again, this can be a little difficult to look at, especially because I'm no artist. So let me draw a different picture, which is what I'll call a side view. And by that I mean the view in the YZ plane. So pretend that we stand over here somewhere along the x-axis and we're looking at the region like this. What would we see? Well, I would see a pizza slice cut out by this red line, the purple cone, and the blue sphere. That's the projection of the region in the YZ plane. And this pizza slice kind of rotates out from the red plane to the green plane. Oftentimes, drawing side views like this can help you think about bounds such as phi. Okay, so now we have a couple beautiful pictures, and what we need to do next is figure out how to describe the region E in spherical coordinates. So to be precise, we want inequalities for rho, theta, and phi that cut out this region. Let's think about rho first. Just like with polar coordinates, to think about bounds for rho, you want to think about walking along rays emanating from the origin. This is easier to draw and easier to think about in the side view picture. And if I start at the origin and walk, eventually I'll hit the blue sphere. And no matter what angle I head out at, the blue sphere is what determines my upper bound. All of the rays start at the origin, so that tells me that the lower bound is 0, and the fact that the sphere has radius √2 tells me that upper bound for rho is √2. Algebraically, we can pick this up by just taking that blue equation, converting it into spherical coordinates. We'd get rho squared equals 2. Take a square root, and there's your upper bound for rho. Let's think about theta next. Theta is the rotational angle in the xy plane, so I'll look at the picture to the left, and I recognize that the theta bounds are determined by the red and green planes. As I rotate counterclockwise from the x direction, the lower bound is determined by the green plane, the upper bound is determined by the red plane. Now, both of these are things you could probably eyeball. For example, the green plane determines the angle pi/4. And if you want, we could confirm this by going up to the relevant algebraic data, y equals x, and turning it into spherical coordinates. Well, in spherical coordinates, y is rho sine phi sine theta, x is rho sine phi cosine theta. The rho sine phi's cancel out, and this will give us the equation sine of theta equals cosine theta. And in the first quadrant, which is what we care about, this happens at pi/4. All this is to say is that the lower bound for theta is pi/4. Likewise, the upper bound is determined by the y-axis, roughly. We know this corresponds to pi/2, so you can probably eyeball it in this case, but if you want an algebraic argument, go up to the relevant algebraic data, which is x equals 0. Turn that into spherical coordinates, you get rho sine phi cosine theta equals 0. And then since we're letting rho and phi vary, we can assume that those first two terms are non-zero and divide by them. That gets us cosine of theta equals 0, which we know happens when theta equals pi/2. So the upper bound is pi/2. All right, finally, let's think about phi. Phi is this rotational angle from the z-axis. This is where the side view comes in handy. As I start sweeping down from the positive z-axis, the first thing I hit is the purple cone. And then I swoop all the way down to the red line, which is the xy plane. But this tells us that the lower bound for phi is determined by the cone. There are a number of ways you could pick off the exact lower bound. For example, this is also something you can probably just eyeball as pi/4. But if you want an algebraic argument, you could either take the entire equation, z squared equals x squared plus y squared, and convert it into spherical coordinates. Pi/4 would eventually pop out. Or even in my side view picture, we could take the induced line equation, which is z equals y, turn that to spherical coordinates. We'd get rho cosine phi equals rho sine phi sine theta, but in the yz plane, theta is pi/2, sine of pi/2 is 1. So we get the equation rho cosine phi equals rho sine phi, kill off the rho's, do some simplification, and we get tangent phi equals 1. Like before, we know this happens when phi is pi/4. So that's an example of an argument that you could give, but like I said, there's a number of ways that you can make this conclusion. In any case, the lower bound for phi is pi over 4. Again, the upper bound is determined by the xy plane, so we sweep down at an angle of pi over 2, and that'll be our upper bound. And with that, the hard part's over. We can take this integral, completely transform it, and evaluate it. So I'll blaze through this part. This will be easy. We start off with this integral of 1 over x squared plus y squared plus z squared. Turn it into spherical coordinates. Now, one good comment to make is that typically you'll set up these integrals in the order rho theta phi or rho phi theta. Usually rho will be first. Not always, but if you're dealing with a region and you decided to use spherical coordinates, there's a good chance that it's radially simple. Otherwise, you maybe would have picked something else. So for now, I'll just write rho theta phi. And if you look at the bounds that we've described, they're all constants, right? So we don't have to worry about interchanging orders in any non-trivial way. We can write this order however we want. Now the integrand turns into 1 over rho squared. And then when we change the differentials, I have to multiply by the Jacobian. Like I talked about previously, the Jacobian is rho squared sine phi. Those rho squareds cancel out, and then we have a very straightforward integral to evaluate. There are no rho's anymore, so when I integrate with respect to rho first, I'll just pick up a factor of root 2. Likewise, there are no thetas, so when I integrate with respect to theta, I'll pick up a factor of pi over 2 minus pi over 4, which is pi over 4. And then finally, we have some calculus to do. The antiderivative of sine of phi is negative cosine phi. Evaluate that at pi over 2 and pi over 4. Cosine of pi over 2 is 0. Cosine of pi over 4 is root 2 over 2. So in the end, we'll get a positive blah, blah, blah times root 2 over 2, which simplifies to pi over 4. Okay, this next example is a little more interesting. Here I want to set up an integral in spherical coordinates that gives the volume of some region. It's the region above the plane z equals 3/2 and below the sphere x squared plus y squared plus quantity z minus 1 squared equals 1. I'll give you one guess as to the first thing that I'll try to do in my solution. I'm going to try to draw a picture. And just like in the previous problem, drawing the three-dimensional picture is going to be a little hard for me, so I'll draw a side view, which is also more helpful, I think. Anyway, here's the three-dimensional world. The plane z equals 3/2 is an horizontal plane that just sits at height 3/2, so I'll draw this in blue here. And then we have this sphere. Looking at the equation, I can see two things. One, that it's centered at the point 0, 0, 1, and the other that it has radius 1. That tells me that the center of the sphere is a little bit below the blue plane, and it maybe looks something like this. So the blue plane cuts through the sphere, and the region that we're interested in is this little cap above the plane contained in the sphere. I think drawing a side view picture is a really good idea here, especially because it captures pretty much all of the geometric information that we need. So again, by a side view, I usually mean something like in the xz plane or in the yz plane. Doesn't really matter in this case. But from the side, we would see the blue plane. It would look like a line, and then we would see the red sphere, and from the side, this looks like a circle. The center of the circle is a little bit below the blue line, and the region we're interested in is the stuff above the blue plane, below the red sphere. Okay, and so now we need to describe this region in spherical coordinates. We need bounds for rho, theta, and phi. Let's think about rho first. Now, as usual, when you think about a bound for rho, you want to think about starting from the origin and walking in a ray emanating off at some angle. And what I'm doing when I think about this is I'm looking at my pictures and identifying which piece or which surface defines the lower and upper bound for rho. So for example, when I walk from the origin, the first thing I hit is this blue plane. That tells me that the lower bound for rho is determined by this equation, z equals 3/2. So I've visually identified the lower bound, and somehow we need to take this and turn it into an algebraic bound for rho. The strategy here is exactly the same as it was in polar coordinates. We use the picture to identify the relevant piece, and then once we do that, take the algebraic information, turn it into spherical coordinates, and solve for the variable that we care about. So in this case, the equation z equals 3/2. This turns into rho cosine phi equals 3/2. And then because we want a bound for rho, I'll just solve for rho by dividing by cosine. And there we go. So the lower bound for rho is given by 3/2 cosine phi. Looks a little weird, but that's okay. Next, we want to think about the upper bound. Well, based on my side view picture, I can see that I stop walking once I hit the red sphere. So the red sphere determines my upper bound. I'll do exactly the same thing that I just did. I'll take the relevant algebraic equation, which is x squared plus y squared plus quantity z minus 1 squared equals 1, and I'll turn this into spherical coordinates. Now, I can see that probably a good idea is going to be to multiply out this z minus 1 squared quantity. When we do that, we'll get a z squared minus 2z plus 1. Looks like I wrote an h there, but it really says plus 1. Those plus 1s on both sides cancel out, and then I can take that negative 2z term and move it to the right. Then easily transform everything into spherical coordinates. The left-hand side, x squared plus y squared plus z squared, that's rho squared. And then 2z on the right turns into 2 rho cosine phi. Divide both sides by rho, and the upper bound pops out. Rho equals 2 cosine phi. Phi is going to be the harder bound, so let's think about theta next. Theta is pretty easy in this case. If you look at the shape in 3 dimensions, I can see pretty clearly that I'm going to take theta from 0 to 2 pi to swoop out the whole region. Maybe one precise way to say this is that if I project this region into the xy plane, it lives in all 4 of the quadrants. It's not contained in just the upper half plane or just the first quadrant or something like that. Because of that, it's going to take an entire range of 0 to 2 pi to swoop this all out. So there are no restrictions on theta. I'm just going to send theta from 0 to 2 pi. Okay, let's think about phi next. Look at the side view picture again. Phi is the angle from the positive z-axis down to the points we care about. So because our region contains the positive z-axis, in part at least, that tells me that the lower bound for phi will be 0. The upper bound for phi is going to be dictated by this intersection point. So I swoop down until I hit this orange ray. That's what will determine my upper bound for phi. So one way to say this is that the upper bound for phi is determined by the intersection of the red and the blue things. Well, the red thing in spherical coordinates has equation rho equals 2 cosine phi. That's what we just found up there. And the blue thing in spherical coordinates has equation rho equals 3/2 cosine phi. So if I want to determine their intersection, I can set them equal to each other since they're both equal to rho. This will give 2 cosine phi equals 3/2 cosine phi. And here we have an equation only involving phi that we can solve, and that'll give us the upper bound. So I would multiply the cosine over, divide by 2 on the left, and this will give us cosine squared of phi equals 3/4, which means cosine of phi has to be root 3/2. And a good technical question is, how do we know it's not negative root 3/2? Why am I taking the positive square root? Really, the answer is because I can see visually that phi is going to be an angle between 0 and pi/2. And in that region, cosine is positive. So because of the geometry, I know that I want a positive square root. And then from there, it's a matter of knowing your unit circle. Cosine of pi/6 is root 3/2. So there's our upper bound for phi. Phi is pi/6. And with that, we're pretty much done. We just have to set up the volume integral. The problem says we don't have to evaluate it, and then we'll finish it off. But as usual, the volume of this region E, abstractly, it's the triple integral over E of dv. And then when I write this in spherical coordinates, the bounds for phi and theta are constant, so it doesn't really matter what order I write them in, but since the bounds for rho depend on phi, we want to make sure we put that integral inside. So the integrand 1 turns into just rho squared sine phi after we include the Jacobian. Then I get a d rho integral, then I'll put theta next, and then phi, but again, theta and phi can be interchanged. The most important thing here is that your rho integral is first. And if you get bored, you could try to actually compute the integral, but beyond that, we are done.